Okay, good afternoon. I'm Christina Gerber. I'm with Suez. I'll be your moderator for this afternoon. And I'm here to introduce Chris Muller. Chris Muller is a principal engineer at Brown & Caldwell in its Boston office. His specialties include anaerobic processes, digestion, biosolids, sludge minimization, process efficiency, planning, bioenergy, and co-digestion. He received his master's and PhD in engineering at Virginia Tech in the study of biosolids flock and stability. Chris is active in regional and national organizations. Please welcome Chris.
Thank you. I'm going to try to stick this thing up here because I'm going to drop it or cause a problem. So the talk I submitted here was called Advanced Digestion Processes, Pairing the Processes with Your Planning Goals. And boy, that was a broad topic. So I'm going to narrow it a little bit. And I'm really going to kind of set the table of where we're going to, where we are today. What are the things that we see in our planning studies that are driving people in different directions? Things that they're concerned, and then give a couple of examples of how different approaches have been used to meet some of these challenges. And then kind of what about tomorrow? As a nerd, I can't help but talk about a little bit of research. So I'm going to throw a little things that we're doing in there at the end. So if we look at digestion, the goals have always been continually evolve, and it's to meet the market demands. And I know we heard the presentation this morning on biochar, and that's maybe the future here. But digestion's been around for a long time, whether we wanted to do it or not. With pits and lagoons and whatnot, but it's moved forward. And as we move from stabilization, mass reduction, all the way through pathogen reduction, and then today we're looking at something that's more in the line of a. There we go. We're looking at things like resource recovery, more sustainable operations, nutrient recovery, enhanced energy production, and then also some just plain economics, revenue generation, and all those things are starting to drive us to do more things with our digesters. And and one way to think about this is it came from a discussion I had with this gentleman Paul Cadota, who's the head of innovation at Metro Vancouver. And this I thought was a great quote, because this is kind of where I think we are, as an industry on the solid side, really should be thinking about going, right? We're trying to promote a circular economy, means we need to upcycle our outputs. That means we got to make things that people really want and that have an intrinsic value. So when we're starting to do our biosolids master planning, it might be that we have to change our outputs or inputs or endpoints to make sure that we, are looking at something that is going to be more sustainable in the long term and actually help control costs. But when we look at solids planning, it's not just the little digester in the middle, and that's my favorite part, and that's what I want to think we all think about every single day, but that's not true. It's truly an end-to-end decision-making process. You've got to know what you're doing up front, what you do in the middle, whether it's a digester, pyrolysis, incineration, whatever it is, and then what you can do on the backside with those products, and then how they all interact. So it's really a full circle analysis that we have to have. And if we do that full circle analysis, it does change. And what we've seen, and this is kind of maybe a little bit the first graphic, maybe a little pictorial way, but when I started, this was kind of a lot of the answer. How's that not working? To the biosolids, right? We produced some sludge, we digested it, put it in a truck, hauled it off to landfill, maybe we incinerated it, or put it on the ground. And that was pretty standard fare. People are starting to say, hey, we can do more with the gas. We're moving away from CHP. People are looking at CNG. It has a high intrinsic value. It has, that's going to generate revenue. We had a project in St. Petersburg, Florida, where over 20 years was going to save $35 million for them. So now, all of a sudden, this product becomes valuable, and this product influences the decisions we make here. So what are we going to do to make that? And then we're seeing people going towards product-based endpoints, right? We've got things like Bloom coming out of DC Water, Loop out of King County. Nashville's got, what was it? Nashville Gold or something along those lines. Bay State Fertilizer out of the MWRA. There's a product or labeling of this material. It's not just sludge to get rid of. And so we're seeing that, and we're getting soil amendments like really successful ones like Tegro, the biochar that I mentioned. And then also we're going to start to harvest nutrients. Our decision on digestion will impact that. How aggressive it is, what we put into the digester may impact how much we can get and how much return we get. Other things we saw with the WRF presentation this morning, new technologies like hydrothermal liquefaction are coming to the market. Making biocrude. Is a slow oil amendment the right product, or is it a biocrude? It was mentioned Metro Vancouver is looking very heavily at this. They actually have a refinery whose team with them was very interested. Can they take a crude product generated from sludge and turn it into a valuable product? But then there's, oh, hey. Sorry, it just froze up. So anyways, we can always move forward. So the last point that I was going to make is the other side of that is there's also the revenue side, and that's the co-digestion. We see a lot of that in the industry, but I don't see I haven't seen a master plan in the last 5 or 10 years that has not included some element of that, and that is because it generates revenue, then it generates gas, and those get into the other products that we can produce. So matching up our system to make that work is important. But also we have other challenges. You know, the byproducts of modern living are shown up in our biosolids, pharmaceuticals, personal care products, all of these CECs. Whether concern is warranted or not, that I think a lot of this is still out for debate, but those are going to drive some of our product decisions. And so what does our process do to that? And then finally, too, you know, what we've been asked to do over time, too, is, you know, to kind of teach an old dog new tricks with time. Solids process has kind of lagged behind a little bit on the liquid side, and then it's always been very empirically driven. We've moved forward a lot of the time just based on what we've learned before. And what we see is that, you know, these might be the limits that we see today, but when you look at getting design guidance, and these are all the different, this is just for mesophilic, these are all different design documents. We've got some saying you can design mesophilic digesters way down here. You know, Washington State's Orange Book says, hey, you can load it all the way up here. Where do you get some consistency on that? And I think some of that's going to come from better tools, but then it's also, we want to be able to take advantage of these higher loading rates and higher capacities going forward so we can intensify our process and basically use our infrastructure more effectively. But when we do this, it has to be a full circle analysis, and, you know, making a decision to go to from mesophilic or up to some of these more advanced digestion processes, we've got to start thinking about how the other systems are impacted, whether it's the thickening. You know, if I want to do THP, I really can't feed it down here at 5 or 6. It's got to be 10 plus. Even thermophilic, to really effectively get it up into the ranges where you're going to get the maximum value, you need a thicker solid. So it's those types of questions. Gas management systems, all the other ancillaries that go into that. So there's quite a bit of factors that go into intensifying the digestion process. It's not just kind of turning up the temperature or doing something, adding a widget to it. So how are people meeting those challenges today? And this is where I kind of realized the roadmap was a little too big for this presentation, because if I went through every single technology in the world out there, we'd be here the rest of the day. So, and since you guys don't all want to hear me talk all day, I'm going to cover a few, but I think what I want to do is kind of give you an overview of maybe the different ways that people have addressed this, and how do we've gone from, say, our conventional digestion processes to more advanced, and what are the approaches that people have used. And really, you know, it comes down to, you know, we can manage the kinetics, move away from a CSTR, move to a plug flow reactor or something along those lines, or series reactors. Manage the metabolism. You know, the easiest way is turn up the temperature. While the earth is getting hotter, not a good thing. Turning up the digester is a good thing if you want to do more with it. Engineering the ecology. And what I mean by that is there is a lot of work being done to select for the microorganisms, do the work that we really want to have done, not just kind of stick it in the soup in the back end and make it let it do its thing. And that's been the very traditional approach. It's more, all right, we know these bugs do this work, let's make them do it and then get somebody else to do the rest of it for us. And the last one, you know, and this one's a hot topic, and there's 2 more presentations on that topic, so I'm not going to cover much details. Pre-treatment is to change the physical and biochemical nature of the sludge by adding something to it or doing something to it, like heat, chemical, or something along those lines. So if we put that into a list, you know, on the digestion side, and I'm not going to cover all of these, I'm going to cover a few. And the way I wanted to cover those with one is they address some of the specific challenges like CECs or bringing in advanced digestion or co-digestion substrates, so they're a little bit unique. But there's lots of ways to do this, and it really, not one of these is going to be the magic bullet. It's going to be the solution is going to be site specific, and it's going to be specific to what your market and the products you want to produce are going to be. And so this was a map I was working on, and I was telling Bill Barber that I hadn't updated this one as well. And this is my little map of advanced digestion facilities, and I'm going to have to start taking off the labels because we're getting too many. But when I first started this, there was a lot of series, thermophilic, TPAD, acid gas, and those types. And then in the last few years, all of a sudden, all these yellow ones showed up, and those are all the thermal hydrolysis. So the adoption of advanced digestion, this intensification, is an approach we're seeing going forward. But it doesn't mean some of the tried and true aren't still impactful. But it's nice to see that map getting a little more dense. And I'm sure there's a few on there that I've missed. Go from there. So one of the first ways I wanted to talk about enhancing the digestion process, and this is something that I've got a little case study from Frederick-Winchester here to go with this, is a newer approach. Well, it's not new, but it's being newly deployed and purposefully deployed for enhancing digestion, is recuperative thickening. And really what it is basically we make our digester look more like our secondary system. We're putting some sort of clarifier, solids liquid separation, in line with the digester and decoupling our HRT and SRT. So the way the process flow works is you have your sludge going in, or high strength waste, and sludge going into the digester. We pull a slipstream out, we thicken it up, we put the thickened material back in, and dump the water out the bottom. So basically now we're truly operating on MCRT basis, which our 503 regs were written on, so we can still get Class B with it. But it allows us to basically keep the mass in there and move the water out, because we really don't care about the water. Now, the challenges with it does increase the process complexity and some chemical use. You've got to use some polymer here. And the odor around here, depending on your process, can be significant, so you want to make sure you have it odor controlled. But it does provide some very benefits, and that's why I wanted to talk about Frederick-Winchester a little bit. This is a plant that's got 2.5 million gallons of digester capacity. They have a very significant co-digestion program. And they started out, and over here on the left, we've got, sorry, glasses. Sorry. SRT or HRT, and then high strength waste load. So over here on the left side, this is where they started their program, and they're basically operating as a conventional CSTR, bringing anywhere around 20 to 30,000 gallons per day of high strength waste in. And what they wanted to do, and what you saw, they were operating somewhere around 20 to 25 days. And they were always designed to operate in this recuperative thickening mode. And around August of last year, they started that process up, so they could go from that 20 to 30,000 gallons per day of high strength waste, which is a lot of it's liquid, to 40,000 gallons per day. And what that allowed them to do is essentially maintain their SRT at that 20 to 25 days, but take in a lot more material. And that, on a 15,000 gallons per day basis, at like say 6 cents, just as a rough number, that's about $300,000 a year of revenue for them. So that's not a bad thing on top of the gas benefit. What also that you see is, like, had they not done it, and this is what I try to show here, is if they had not gone through that process of taking the extra water out, putting the thicker sludge back in, they basically then would have gone down, drifted down below that, right near that 15-day mark or below. So challenging their biosolids quality, but also the stability of the process itself. So this was, it's a different approach than we typically think about digesters. Most of us think of it as a complete mixed reactor, but this is a good way to kind of look at its overall, capacity and not having to do something that exotic. Really, what's interesting is in a lot of these facilities, and we're designing a couple more of these, one in Derry Township and one in Montpelier, Vermont, the thickener that works for your WAS works just fine as the thickener for this. You don't have to have a separate one. You just maybe have a slightly bigger one so you can process this stuff through the day. But in terms of, the question of what does it do to stability? Well, when we looked at the process, the alkalinity is hovering around 4,700. Volatile acids are a little elevated, but that's not, at that level to me, that's not of concern. I mean, we've seen higher and this thing still works, and the ratio is great. But the other thing we see is a great stability in the, a pretty good increase in the VSR. Some of that's probably due to the high strength waste being brought in, but it's fairly consistent. It's not as scattered here. The other thing I noticed too when I was looking through this data here was that the process actually seemed to be less noisy. The day-to-day HRT was less noisy, so it's actually going to be a little bit more stable. It's not going to, digesters like to run stably, and that's because by essentially you're decoupling that hydraulic load from the front end of the plant a little bit further by having this kind of clarifier in the back end. So you're having a little bit more SRT control, which is interesting. So this has been a very successful approach, and it's one that can be done for most any plant. And in terms of loading rates, we're still kind of working them out, but maybe you can operate at about a 10-day HRT with a 20-day SRT. So and then the gas costs aren't that bad. So for that high strength waste differential that they were looking at, I did the math. Basically, if you said it was like a typical high strength waste, it comes out to be they need about 0.7% TS of that high strength waste to be used to make the gas that they need. So if you had 10%, that means I get 9.3% for gas production, and I have only that small margin basically for the lost heat, because that's always a challenge with it, is when you have that, you're heating a whole bunch of extra material coming in. So it's not too bad that way. So on the other temperature side, talking about temperature, that we got to our strategy 2, which was thermophilic. And we've done a couple of these plants more recently, San Jose, St. Petersburg. And thermophilic offers some great opportunities, and maybe that recuperative doesn't. One, you can go to Class A if you want to. It also supports a much higher loading rates. We think it's about double what you can get out of a mesophilic digester. The big challenge is, though, that with these is that they, still are classified as Class B if they don't have a batch tank behind them or some other kind of Class A requirement. But we've seen folks like East Bay Mud get site-specific acceptance as 10-day for Class B. So that'd be one thing if you're going this route, to basically look for energy generation. But look about trying to do that, and so you can really maximize the benefit of the process. Pretty much if you hit 15 days, you're not going to get as much benefit out of that. The changeover to this process is lost to a degree if you hit 15 days and you want to stay Class B. But what we can see in general, this is a number of plants that have converted over from mesophilic to thermophilic. We do see a pretty significant increase in VSR. It's about 15 to 20% on a basis. And this is for T-pad with thermophilic, so thermo followed by meso. And what we're seeing on series thermophilic, and this is just basically a series of tanks in a row, we're seeing a little bit higher benefit as well. And for Anaerobic Island, which is interesting, that's the one it's in Canada, actually flow-through series thermophilic reactors are considered Class A. So different rules, but they consistently hit Class A. So maybe there's a technology transfer we can have someday to get that brought here. But thermophilic, it's going to give you a lot more capacity. It's going to potentially give you a road to Class A. The big challenges are you're typically going to see an increase in the polymer demand. People report it as high as 20 to 50 pounds a ton, because basically it does such a good job breaking down all the sludge. It makes a whole bunch of colloids, and those colloids are in solution. Now you need a whole bunch more polymer to pick it back up and bring it back into solution. You're going to have a higher heat demand. You're going to need about 30% more heat. So if your gas is high value on RINs, maybe you don't make this decision to go thermophilic. You have to kind of do the math and balance that out, right? Because if I have to burn more of my product gas just to make heat, I got to make sure I'm actually loading it heavily enough to do that. And the same thing on the Class A. It's not, if you don't need it, maybe it's not worth it. But it does let you. The only real benefit with going to Class A, it would let you deviate from the core HRT requirements for, say, a PSRP of 15 days without any kind of discussion, because that requirement goes away once you hit Class A. The nice thing about thermophilic processes in general, the product quality odor is lower. Doesn't mean odor during dewatering is lower. That is pretty high. So you have to have a pretty strong dewatering, odor control in your dewatering system. But what they see in the research is a tendency for that product to have basically a low sulfur odor that doesn't see a peak for a long time during storage. So basically, if you can get it moved out, it's going to be a good quality product. As I said, there's about 30%. That number's wrong, but it's about 30%, not twice. And then, a lot of people spend a lot of time around heat recovery on that. And the challenge with heat recovery on thermophilic is it's typically trying to do sludge to sludge to sludge to water to sludge. And the value of energy these days is still not quite high enough to basically be valuable for a number of processes, or be valuable enough to basically warrant a highly complex system. Like as an example, Anaerobic Island in the 90s tried to do heat recovery on the thermophilic phase using spiral heat exchangers. Needless to say, they clogged going from thermo to raw sludge. So if you're going to do that, just think long and hard about its value and the benefit to do that. In terms of resource recovery opportunities, thermophilic processes have been shown to digest food waste and fog really well and break them down really well, so it's really good. And since those materials come in at much higher concentrations, it really does effectively use that volume much better than, say, sewage sludge, which we keep trying to around 6 or 7%. So seeing that I've got a little bit of time, the other one I wanted to touch on here was, and this one I find quite interesting, because this is one of the ones that first really starts to integrate a whole bunch of different process elements into it, is this post-aerobic digestion. I think it's based on some principles that were done at Virginia Tech with DC Water, and basically it's based on the principle that some sludge breaks down under anaerobic conditions and some sludge breaks down under aerobic conditions. So if you combine the two, you're going to get overall better solids destruction. And that's what we're seeing with this process. I think it's very interesting. I think the big challenges are surrounding this reactor and getting all the benefits that it potentially have worked out for you. But in terms of performance, this is some data that we pulled from different facilities, but 80% VSR, 32% in the post-aerobic phase on another one. So if you add, say 50% on top of that, you're getting pretty significant numbers. Boulder's getting 62%. So these are big VSR numbers, but I think the bigger thing is by adding the aerobic phase, you kind of also start to address the nutrient issue. And if you're going to do some, if you have nutrient requirements, that's an added benefit. It's saying 90%. Meridian was 81%, 93%. So maybe not 100% removal or as high as efficiency as like Anamox or something like that. But at the same time, if you can knock it down and make it more treatable in the mainstream or not need a whole second side stream, and then you get all these additional VSR benefits, it may work out overall better for the as a better choice for you. What I think is really some of the more interesting things that when we're reviewing this and looking at this is that we're seeing reduction in polymer demand with it, so there's some added benefits. So it's really a big picture discussion around it. There's an odor reduction, especially when it follows a mesophilic digester, not so much when you're following a thermophilic. And the same thing with the polymer demand. Thermophilic doesn't seem to be as impacted. The benefits aren't there as much. But the other one that really struck me, this is one of the few digestion processes that I've come across that will say significantly reduces estrogenic compounds, which was interesting. Typically when you put a sludge in an anaerobic digester, you don't see much reduction. You maybe see an increase because some of those compounds, as they break down, they become more estrogenic in nature because their byproducts are more reactive. So that was interesting. But there are some energy considerations. You are aerating, and what we're finding too is when you aerate thicker sludge, it will auto heat. Sludge likes to heat itself. So there is some of these facilities now integrating and cooling on that side, so there's an added cost there. And I think it was one of the presentations that I sat in on, so the vendor tech is sitting right around $50 a wet ton. So if you're sitting in that range, this is where it starts to make sense. Obviously, there's some electrical rates that are very market specific that would drive that up or down one way or the other. Like where I am, I've got clients with 14 cents a kilowatt, 2 minutes. All right. So really, what we're seeing is that, when we look at different technologies and different approaches, it doesn't always have to be one, there's not one magic bullet here. And when you go out and you look into your market and do your planning, all of these processes, all these elements here on the far right side really are going to dictate what's going on in here. And then also opportunities here on the market side. I think that's where we're sitting and that there's a lot of different approaches to doing it. There's not going to be one magic bullet for that. Now, as I said earlier, I'm very nerdy and I had to say something about things new. These are technologies that people are looking at. This is some work that's being done in Metro Vancouver on microwave advanced oxidation. And this is kind of like Canby. It's going to be a pre-treatment. And they add hydrogen peroxide and microwave to swaths in this reactor here, and basically it breaks down the sludge. And that's before treatment, and that's post-treatment. And I unfortunately don't have a movie, but this basically doesn't move, and the other one basically behaves very much like water. The exciting side of that is I think, the oxidative power of the peroxide in the microwave may break down some other compounds as well, not just giving you overall enhanced sludge production. We'll see where this goes. Right now, the reactors are this big, so we're a ways away. Another one, and I'll cover it in 3 seconds, but is they're looking at is what I'm calling thermophilic temperature phased anaerobic digestion. Basically, it's taking the front end of TPAD and jacking the temperature up to about 70 degrees C. And why do they want to do that? Because usually that kills everything. Some of the research they've been looking at is basically seeing that at those temperatures you get a very high hydrolytic rate, and that's typically the rate limiting process in digestion. So maybe biologically do something very similar to what THP does, is basically have the bugs work very well in simplifying the substrate, so when you put it into a regular mesophilic digester, it goes off like that. But it's a biological process rather than a physical chemical process. And some of the research is showing they're getting some pretty good enhancements, 10, 15% over the conventional. So it's going. Again, those are also in reactors that are this big right now. They're hopefully going to be doing a full scale or a demonstration scale. But with that, I'm going to stop. Any questions? No? Well. Yeah.
That you could run 15-day HRT and 15-day SRT, or 20-day SRT.
Right.
Would the EPA, when they look at that, did they consider that still class B for HRT, just dead rays and not 15? I'm just curious.
Well, yeah, my reading of the regs, and I don't speak for EPA, but my readings of the regs are written on MCRT. So you can, it is, you're treating the solids and not the water, and the water is recycled back. So as long as the solids are in there long enough, then it should be fine.
So, and how much were you able to see feasible of thoughts and instructions?
It was a little hard to ferret out what exactly the attribute was there. I mean, you're going to get some benefit just from longer retention time. You are getting up in the flat part of the curve. But if you're moving to 15 to 20%, that's on the that inflection point of the curve. So you might see a few points there. But in terms of what they saw there, Frederick-Winchester saw from getting say 50% to 56%. I'm a little hesitant to attribute that just to recuperative thickening, because they also brought in another 15,000 gallons of high-strength DAF sludge, basically. So if that has an 85% VSR, that's going to naturally skew your number higher. So I wouldn't feel comfortable saying, yeah, you're going to get 10 points more.
Thanks.
Yeah. Oh. Yeah. 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 No, the work they're doing it at 70 degrees C doesn't kill everything like thermal hydrolysis. It's just trying to get at the same intent of basically taking a very complex submatrix and breaking it down to something very simplified that allows you to accelerate the next phase. So it doesn't sterilize the material like THP does, which makes a challenge for startup. Yeah. Bill?
So one of my last blogs had to do with odors, biosolids, and one of my pet peeves is that we don't really have a standard way of characterizing the final product depends on all these different processes.
Yeah.
Do you find that some agencies, especially those that are experimenting with new types of advanced injection, are actually characterizing the final product for odor intensity for the purpose of helping to inform
the user?
Evolving technology?
Yeah, some of them are. I mean, the DC Water's done extensive amounts of testing. Metro Vancouver, actually, we were doing a baseline analysis for their Lulu Island plant, and part of that we characterized the plant's operations plus all the digester operations and whatnot. But we did do sampling on the biosolids product as is, so we could then have a baseline. Here's what the biosolids product odor quality looks like. And so when they do any testing on in their phased analysis here, they'll be able to say, this is what it was before and this is what this is after. So yeah, people are looking at that from, some folks are. Because it is a big issue. I mean, I've had clients tell me stories of we've driven empty trucks by houses and we get odor complaints for empty trucks. So, you know, being able to characterize and what's going to happen is important.
Frederick-Winchester, did they have a characterization of the odors?
I don't know. I don't believe so. Any more? Cool. Thanks.